Hi, this is week 30 of chemistry, and we'll be looking at the third lesson of unit 6, which is chemical thermodynamics. In this lesson, we'll focus on physical changes. For our lesson objectives, students will be able to calculate the amount of energy required to heat an object through multiple phases, from solid to liquid to gas. Let's get started.
Now, let's go ahead and begin our conversation on phase change calculations. Now, we're going to begin by talking about that ice cube you see on the screen for the picture. It's melting, right? But does it just instantly, once it reaches a temperature of 0 degrees Celsius, its melting point, does it instantly just poof, turn to water? And the answer is no. It takes both time and energy. It takes heat to go ahead and go through a phase change from solid to liquid. Same thing for water that is boiling. If you're ever cooking and the water is boiling, does it instantaneously, poof, turn out to steam? The answer is no. It takes a lot of energy. Now, how do you calculate the energy you need to? That's the equation that's up on the screen. Q, which is energy, is equal to mass multiplied to something called enthalpy. So that's the equation we'll be looking at. Now, let's look at it a little bit closer. All right, now, what is enthalpy? Enthalpy comes in two things: enthalpy of fusion and enthalpy of vaporization. The first one we're going to look at is enthalpy of fusion. So the change from solid to liquid is called the enthalpy of fusion, also known in some books as heat of fusion, either one. So the value for it when you're turning a solid to a liquid for water is going to be 334 joules for every gram. That's the enthalpy of fusion. That's the energy. So for every gram of ice, you're going to need to supply it with 334 joules of energy to change it from a solid to a liquid. Now, enthalpy of vaporization, that is the change from liquid to gas. So to get it to evaporate, that's what it's called, enthalpy of vaporization. Again, in other books, you might refer to it as heat of vaporization. The energy you need to turn a liquid to gas, and this is for water, is 2,260 joules for every gram. So for every gram of water you want to evaporate, it's going to require 2,260 joules of energy. All right, so that is the enthalpy of vaporization and enthalpy of fusion for water. Those are their values. Why is vaporization so much bigger than the enthalpy of fusion? For water, one's 334 versus the other one's 2,260. Why is there such a big difference? It has to do with the space you need in between the molecules. So when a solid, it needs to be turned into a liquid, the molecules only need to be separated slightly, just enough so that one atom can get past another. But when a liquid needs to be evaporated, turned into a gas, the distance between molecules is much, much greater, so therefore you need a lot more energy. Now, a couple of other values that are important to know before we start doing our phase change calculations. The specific heat of water changes depending on what phase water is in. Let's start at the very bottom. When water is a solid, and when you have a block of ice, the specific heat of water is 2.1 joules per gram times degrees Celsius. When water is in the liquid phase, it is 4.2 joules per gram times degrees Celsius. And when water is in the gas phase, then the specific heat of water is 2.0 joules per gram times degrees Celsius. So specific heat of water is going to vary depending on the phase, the physical state that the water is in. All right, now let's go ahead and take a look at some examples and solve some problems involving phase changes and heat changes.
Let's go ahead and take a look at example 1. In this problem, we ask the following question. Calculate the amount of heat required to convert 25 grams of ice at -50 to steam at 140 degrees Celsius. One of the things I like to do is to go ahead and do a graph with information that's there. And the reason why I like to do that is because it helps you visualize when you have a solid, liquid, or gas. Again, the 0 and 100 represent the boiling point and melting point for water. So that is where the phase changes happen. All right, so I'm going to go ahead and do a very rough graph of what we see here. We're starting at -50, so if this is 100, that's 0. -50 is around here. And this is a rough graph. It's more for you to figure out whether you have a solid, liquid, or gas. So don't really get too hung up on how accurate it is. It's a rough graph. I'm going to start around here at -50, go up here. Now what happens at 0? Solid begins to melt. So it takes a little bit of time. So I'm going to draw a line that is horizontal. Then from there, I'm going to go ahead and the temperature keeps on climbing, and it will climb all the way to 100. Why is that important? Because at 100, that's when a solid turns to gas. So therefore our line will go flat again. And then finally it will go ahead and keep on climbing somewhere around 140, which will be somewhere around here. So let me go ahead and write down their values. 0 right here and negative 50 here. Next, which formula should we use? We got two formulas. For lines going up and down like here, there, and there, we go ahead and we use this formula with a phase change. Now I use a little bit of color coordination. For the amount of energy is equal to the mass, which we have is 25 grams. The change in temperature, I would just subtract the final minus the initial for each one of these sections. And the C, which I have it here in blue, refers to the specific heat, in this case of water, at different temperatures. So for example, if we have it at this section, that's in the gas phase, so that's going to be 2.0 joules per gram centigrade Celsius, as opposed to this line will have liquid section, so therefore it'll be 4.2, or this line which will be solid, which will be 2.1. That's the value of the C. Now for the flat lines here and there, that is where we're going through a phase change. So we use this formula right here, which will be mass multiplied times the enthalpy. The enthalpy of vaporization is 2260. That's when you're going from a liquid to a gas. So you see here liquid to gas. And when you're going from a solid to a liquid, that will be my enthalpy of fusion, which is when you go from a solid to a liquid, and that is 334. All right, so those are the values. Now I'm going to go ahead and start solving for the complete amount of energy. So we're going to do one line at a time. So this will be line 1, 2, 3, 4, and 5. So I'm going to begin at the very top. And for this one, it's going to go ahead and be line 1. I'm going to use this formula because it's a line going up and down. So I'm going to label that as Q1 is equal to mass, which is 25 grams, multiplied times the change in temperature from 100 to 140, we went up 40 degrees, multiplied times the specific heat. Line number 1 is in the gas phase, so I use for gas phase 2.0 joules times grams times degrees Celsius. Alright, we'll have to solve for the numbers, we'll probably put them elsewhere. Alright, Q4 number 2, that's this flat line right here. So since it's a flat line that's between the liquid and gas phase, we're going to use this smaller formula, which is the mass, still 25 grams, multiplied times, we got to pick enthalpy of vaporization or enthalpy of fusion. In this case, going to be is between liquid and gas, so it's enthalpy of vaporization, the 2260 joules per grams. All right, line number 3, that is from here to there. All right, it's going up and down, so we're back to this formula. Mass still 25. It remains 25 throughout the whole problem. The change in temperature from 0 to 100, it is 100 degrees Celsius. And the liquid, see line number 3 is in the liquid phase. So for which specific heat to be used? Well, when it's in the liquid phase, which is 4.2 joules times grams centigrade Celsius. All right, next, line number 4. Line number 4 is going to go ahead and be, it's flat, so therefore we go ahead and we use this formula right here, which is mass times the enthalpy. Line number 4 is between the solid and the liquid. So between solid and liquid is enthalpy of fusion, the 334. So I'm going to put Q4 is equal to 25 grams multiplied times 334 joules per gram. And we'll get the answers in a bit. All right, next, for the final part, Q5, it is our line number 5. All right, so it's an up and down line, so we're back to our original formula. The mass still 25. It doesn't change because 25 grams of ice or 25 grams of water or 25 grams of steam are still, they all weigh 25 grams. All right, the change in temperature, starting at negative 50 and it goes up to 0, we went up 50 degrees, so it'll be 0 minus negative 50, so negative and a negative will give you a positive. So it will be just 50 degrees here. And finally, the specific heat for line 5, it's going to be 2.1 because line 5 is in the solid section, so it's going to be 2.1 joules times grams centigrade Celsius. All right, so those are all the values. At this point, what you would do now is go ahead and multiply all of these one by one, and when you want the grand total, you're going to go ahead and add them all together. Let's go ahead and do that now. I'm a little bit out of board space, so I'm gonna get rid of my graph now and put the answers here. Alright, so I'm gonna go ahead and start multiplying. For the first one, it's gonna be 25 times 40 times 2. It's gonna give me 2,000 joules. Next one's going to be 25 times 2260. It's going to give me 56,500 joules. 25 times 100 times 4.2, 10,500. For the third one, 25 times 334 gives me 8,350 joules. And for the last one, 25 times 50 times 2.1 gives me 2,625 joules. To get the grand total, so I'll put that as Q with a T for total, equals, and we would add them up to get the grand total, so begin to add them up, 2,000 plus 56,500 plus 10,500 plus 8,350 plus 2225 will give me 79,975 joules of energy, and that is example number 1. Alright, let's go ahead and move along now to example number 2. In example number 2, we're asked a very similar question. This one says, calculate the amount of heat required to convert 10 grams of water at 35 degrees Celsius to water at 120 degrees Celsius. But at 120 degrees Celsius, it is the element, it is the compound water, but it is in the gas phase. Alright, so let's go ahead and solve that problem. So erase all this data. And let's take a look at our graph again. Alright, so in this graph, again below 0, that is the solid. Between 0 and 100 is liquid, and above that it's the gas phase. Alright, so when we do the graph, where we're going to begin, we have 35 degrees Celsius, so we're going to go ahead and start above 0 and below 100, so somewhere around here. Again, this is a rough graph, and I'm going to go up, up, up till it reaches 100, and in this case I want us to go to 120, so I'll be somewhere around here approximately. And this is 35. How many formulas are we going to need for this problem? Well, there's only 3 pieces as far as the lines go, so we only need 3 formulas. So I'm going to label this one as number 1, number 2, and number 3. Those are it. Alright, so let's go ahead and start solving. Line number 1. Line number 1 is going up and down, so we use this formula. And so I'm going to label it as Q1 is equal to, and the mass is 10 grams. The change in temperature from 100 to 120, that's a 20 degree change. And the specific heat, it's in the gas phase. Gas phase is 2.0 grams, 2.0 joules times grams times degrees Celsius. Alright, next, line number 2 is flat, so that is this formula. Notice line number 2 is between the gas and the liquid. Between the gas and the liquid, that is the enthalpy of vaporization. Alright, Q2 is equal to 10 grams, multiply times 2260 joules per grams. Finally, line 3, it is in the liquid phase, so for the specific heat, we use the one for liquid, 4.2. The mass is 10 grams. The change in temperature from 35 up to 100 degrees Celsius, that is a change in temperature of 65 degrees. And it is in the liquid section, so it's 4.2 joules, 10 grams times degrees Celsius. Alright, again, we get our calculator and solve. Let's see, we have 10 times 20 times 2 gives us 400 joules. 10 times 2,260 will give me 22,600 joules. And 10 times 65 times 4.2 gives me 2,730 joules. To get the grand total, so QT for the grand total, it's going to be 400 plus 2,260 22,600 plus 2,730 gives me 25,730 joules, and that is the total amount of energy to get our water to vapor at 120 degrees Celsius. Let's go ahead and move along next to example 3. In this problem, you ask the following question. So for the amount of energy needed to raise the temperature of 120 grams of ice at negative 50 to 75 degrees Celsius. At that point, we have water. All right, so let me erase the previous example. And also the graph while we're at it. All right, so let's go ahead and draw the graph. We're starting at negative 50, so that is below 0, and we're going to finish around 75. So we're going to go up, up, up here. It goes flat for a bit, and then up to here. That's our final spot at 75 degrees Celsius. This is at 0, and this is negative 50 degrees. All right, so there's 3 parts to this line, so therefore there's going to be 3 formulas. This was part 1, part 2, and part 3. Part 1's in the liquid section. Part 3 is also in the solid section, but line number 2 is in between solid and liquid. All right, so let's go ahead and begin solving. All right, so we're going to begin with line number 1. We use this formula. Q1 is equal to the mass. The mass is going to go ahead and be given to us. It is 120 grams. The change in temperature from 0 up to 75 degrees, that is a 75 degree change in temperature. And line number 1's in the liquid phase. So for liquid, we use 4.2 joules times grams times degrees Celsius. All right, line number 2 is flat. So therefore, it is this formula. And it is between the liquid and the solid. So between liquid and solid, we use the enthalpy of fusion. So it's going to look like this. Q2 is equal to 120 multiplied times 334 joules per gram. And finally, line number 3 is going up and down. So we're back to this formula. Mass and change in temperature are 120 grams. Change in temperature from negative 50 up to 0, you went up 50 degrees. And it is in the solid section, so therefore it is 2.1. All right, so now we're going to go ahead and plug all of those values into the calculator and get our answer. So it'll be 120 times 75 times 4.2 gives me 37,800 joules. 120 times 334 gives me 40,080 joules, and 120 times 50 times 2.1 gives me 12,600 joules. Grand total, add all 3 of them together, and we'll get our answer. 37,800 plus 40,080 plus 12,600 gives us 90,480 joules. And that is our answer for example number 3. All right, let's go ahead and move along. For our next problem is going to be example number 4. And example number 4, we're given, it says an ice cube with a mass of 50 grams at negative 25 degrees Celsius. Figure out the energy to get it to 150. So how much energy is needed to get it to evaporate? All right, so we're going from solid to liquid to gas. So this one will require 5 different equations to go ahead and solve for this. All right, let's get rid of example 3. All right, and again, we have 0 and 100 for gas, liquid, solid. All right, in this problem, we begin with negative 25. I'm going to guess that's somewhere around here, negative 25, and go up to 150. So negative 25, again, it goes flat here, goes up, it goes flat again, and 150, we're going to say somewhere around here. 150 degrees Celsius, here's 100, 0 degrees Celsius, and negative 25 degrees Celsius. All right, so now we got that. The mass is 50 grams as given, so let's go ahead and figure out the energy required to go ahead and solve for this. All right, so 5 different lines. Let me label them so we know what you're referring to. I'm going to call this one on top number 1, 2, 3, 4, and 5 right there at the bottom. All right, next, let's go ahead and start plugging into the formulas. Again, 1, 3, and 5, we're going to use this formula right here. For 2 and 4, which are the flat lines, we're going to use this formula. And we use this one because they are going through a phase change. All right, so let's go ahead and get started. So Q1, the mass is 50 grams. And that's going to remain the same throughout the whole problem. The change in temperature for 100 to 150 is 50 degrees Celsius. And line number 1 is in the gas phase, so that is a specific heat of 2.0 joules over grams centigrade Celsius. Line number 2 is flat, so we use this formula. So it is mass is 50 grams, multiply times. Line number 2 is between liquid and gas. Between liquid and gas is 2,260. Line number 3 is up and down, so we're back to this formula. So I'm going to label it Q3. It's equal to the mass, 50 grams. That's the change in temperature from 0 up to 100. That's a change in temperature of 100 degrees Celsius. And the specific heat, this one sees in the line number 3 is in the liquid phase. So we use the one for liquid, which is 4.2 joules times grams centigrade Celsius. Next, line number 4, it's flat. So we're back to this formula. Mass times the enthalpy. Line number 4 is between solid and liquid. So between solid and liquid, we use the enthalpy of fusion. All right, so it's going to be 50 grams multiplied times 334 joules per gram. All right, next, line number 5. Line number 5 is down here. It's going up and down, so we use this formula. All right, so the mass is still 50 grams. That's throughout the whole problem. The change in temperature from negative 25 up to 0, you go up 25 degrees. All right, and it is in the solid phase, so we use for solid the 2.1 joules over grams times degrees Celsius. All right, again, we get our calculator to get the value for each one of these, and then we're going to add them all together to get our final answer. So it is 50 times 50 times 2. That's going to go ahead and give us 5,000 joules. 50 times 2,260 gives us 113,000 joules. 50 times 100 times 4.2 gives us 21,000 joules. 50 times 334 will gives us 16,700 joules. And lastly, 50 times 25 times 2.1 gives us 2,625 joules. To get the grand total, just add them all up. So let's go ahead and do that. 5,000 plus 113,000 plus 21,000 plus 16,700 plus 2625 gives me 158,325 joules of energy, that's a J, to convert 50 grams of ice at negative 25 all the way to steam at 150. In example 5, we're given the following. It says, calculate the amount of energy needed to raise the temperature of 200 grams of water from 20 degrees Celsius all the way up to 600 degrees Celsius. Now, let's go ahead and take a look at our graphs. At 0 and 100, that is where the phase changes happen. From solid to liquid is a 0, from liquid to gas at 100. So when you draw your graph, it only stops, we start at 20, so it's to be above the 0. We only stop at 100, and that's it. Sometimes students want to stop at 200 and 300 and 400. No. There's no phase change there. It's all the gas phase, so it's a straight line up there. So we're only going to really need 3 formulas to solve this problem. It's going to be line 1, 2, and 3. So let's go ahead and start. So for line 1, right here, it's going to go ahead and be from 100 all the way to 600 degrees Celsius. So I'm going to go ahead and write down Q1. It's equal to the mass, which is given to us is 200 grams, multiply times 500 grams, because that's the difference between 100 and 600, multiply times, it's in the gas phase, so it's going to be 2.0 joules times grams, joules over grams centigrade Celsius. For line number 2, it's a flat line, it's between the liquid and the gas, so we're going to go ahead and use the enthalpy of vaporization, so it's the mass of 200 grams multiplied times 2,660 joules per grams centigrade Celsius. And finally, line number 3 down here. Now that line begins at 20, finishes at 100. So the change in temperature from 20 to 100 is 80 degrees. So the mass is 200 multiplied times 80 degrees Celsius. And the specific heat for it, notice, is in the liquid section. So we're going to use the specific heat for the liquid section, which is 4.2 joules over grams times degrees Celsius. Alright, so at this point, we'll go ahead and get our calculator, plug it all in and solve. So it's going to be 200 times 500 times 2 gives us 200,000 joules. 200 times 2260 gives us 452,000 joules. And finally, 200 times 80 times 4.2 gives us 67,200 joules. To get the grand total, Q total, add all three of those together, and our final answer is going to be 719,200 joules of energy needed to get those 200 grams of ice from 20 degrees Celsius up to 600 degrees Celsius. That takes care of example 5. This brings us to the end of the third lesson of Unit 6. Thank you so much for watching.